In this video, we're going to talk about how to find roots of complex numbers. So nth roots, like square roots, cube roots, fifth roots, seventh roots, things like that. So that'll be the main focus, is finding nth roots of complex numbers, but we will also talk about a little bit of notation and how to find the principal, or how to identify the principal nth root of a complex number. We'll also talk a little bit of how that applies to your calculator as well. So before we can get going with nth roots and how to find them for complex numbers, we need to spend a second talking about how to recognize or when two complex numbers in exponential form are equivalent to each other. So let's say you have a complex number z, which would be re to the I theta in exponential form. And let's say we plot it on the complex plane. So I've plotted z. It lies on this circle centered at the origin with that radius and that argument right there, theta. So notice, though, that if I take that angle, theta, and I add 2 pi, it puts me right back to where I start. So as the angle is increased in the positive direction, this point would move around the circle. And then by the time I added 2 pi to the argument, I would get right back to where I started. Now you could do the same thing in the other direction. I could decrease the angle or move it in this direction, and it would move around the circle until I got back to here. So adding 2 pi or subtracting 2 pi from any angle theta that has a terminal side containing z, I end up getting the same exact point, yet it's a different angle. So what this implies is two complex numbers in exponential form are equal if and only if r, or their moduli, are equal. So if r1 equals r2, and if the second, you could do it either way. So the way I have it written is, if the argument of the first one is equal to the argument of the second one plus 2k pi, where k is any integer, then you have two equivalent complex numbers, although numerically they might look different because the theta value could look different. But if that theta, essentially if that theta has the same exact terminal side as the other complex numbers theta and their moduli are equal, then you have two equivalent complex numbers. So basically what this is saying is, in exponential form, two complex numbers are equal if their moduli, if their distance from 0 is the same, and if theta is an angle that has the exact same terminal side as the other complex number. So if they have the same terminal side and the same moduli. Okay, so with that in mind, let's talk about how to find an nth root. So in the real number system, so real numbers only, we say that a real number b is an nth root of a real number a if b to the n equals a. So b is an nth root of a if b to the n equals a. So just for a quick example to kind of remind yourself, that would be the same thing as saying 4 is a square root of 16, since 4 squared is 16. So just to see like an example of that in action, 4 is a square root of 16 because 4 squared is 16. So that was kind of our working definition for an nth root in the real number system. So let's translate that over to the complex number system. So in the complex number system, z in exponential form, we're going to use exponential form for this. You can do polar form or rectangular form, but we're just going to use exponential form in our description of this. So z in exponential form is an nth root of another complex number z sub 0, or z naught, N-A-U-G-H-T, naught. So z is an nth root of z naught if z to the n is equal to z naught. In other words, r to the n, e to the I n theta would be equal to r naught e to the I theta naught. So it basically mimics the real number system definition. So this complex number is an nth root of this complex number if you can take the first one to that power and it comes out to equal this second one that we listed. Now n has to be 2, 3, 4, 5, 6, 7, so a second root, a third root, a fourth root, a fifth root, a sixth root. And z, the number we're starting with, can't be 0. Z can't be 0. So basically, by not allowing z to be 0, you get distinct and unique roots. Okay, so notice up here that these are equal, so that means r to the n equals r naught. So r to the n would be r naught. And if you solve that for r would be the nth root of r naught. These are real numbers. Remember, r is the modulus. So r to the n is a real number, r naught is a real number. So you just take the nth root of both sides, and you get r equals the nth root of r naught, which would be positive. It's positive because, remember, r is the modulus, so it's the distance from 0, and distance is positive. Well, also notice that n theta would equal theta naught. So n theta would be theta naught. But you can add 2k pi to that and get yet another angle that has that same terminal side. So n theta could be theta naught plus 2k pi, where k is any integer. So if you solve that for theta, you get theta is equal to theta naught divided by n plus 2k pi divided by n, where k is any integer and n is the n we're referring to up here in the root. So basically what we're doing is establishing a way to come up with these nth roots, because we're saying, using the definition, if I can take this complex number, raise it to the nth power, it should come out to be this complex number. And then using that definition, we're just equating the two sides. So r to the n should equal r naught, or r should be the nth root of r naught. And then n theta should be the same thing as theta naught, and then we solve that for theta, and we get this expression. So this makes a lot more sense when you see it in action, and when you see it visually. That's another thing that's going to help quite a bit here. All right, so what that does for us is that yields the following for nth roots. So say I give you a complex number z naught, so a specific complex number, and I ask for the square roots of it, or the cube roots of it, or the fourth roots. Here's how we're going to find them. Those roots will be given by this expression, the nth root of r naught, or the nth root of the modulus of this complex number, and then the angle would just be theta naught divided by n and 2k pi divided by n. That'll be the angle for our nth root, whichever ones we're doing. All right, so let's go ahead and actually see this in action. Hopefully it makes a little bit more sense when you see it in action. It's definitely one of those things where when you do it a few times, it becomes a little bit repetitive, and you start to kind of see how it's working and why the picture ends up looking the way it does for these. So let's start by finding the cube roots of negative 8i. So we want all the cube roots of negative 8i. So basically what this is asking for is we want all z such that z cubed come out to be negative 8i. That's what they're asking us. We're supposed to come up with all the complex numbers that, when cubed, come out to be negative 8i. So I recommend doing this with exponential form. So let's go ahead and convert this to exponential form. So on the complex plane, negative 8i would be down here. So let's say that's 2, 4, 6, 8. So this would be the angle in standard position that corresponds to it. And let's just do its principal argument as our first angle. So its principal argument would be negative pi over 2. So negative 8I in exponential form would be its modulus, its distance from 0, would be 8. So it would be 8e to the negative I pi over 2 power. That's using its principal argument. It's using its principal argument. But there are lots of angles that have that terminal side. So in exponential form, we have 8e to the I negative pi over 2 plus 2k pi, where k is any integer. So that's its exponential form. So we now want the cube roots of that. So to find the cube roots, we're just going to use our result from up here. The cube roots will just be, we're going to take the cube root of the modulus, cube root of r, and then we're going to take the angle, which is negative pi over 2, divide that by 3, and then we're going to take 2k pi and divide by 3. Come up with the cube roots. So our cube roots, which would be n equals 3, are going to come from the cube root of r, which was 8, e to the I, and then it's going to be negative pi over 2 divided by 3 plus 2k pi divided by 3. Where k is any integer. So let's start with k equaling 0. Let's see what that gives us. So when k equals 0, let's see what we come up with. We have cube root of 8, e to the I, well, let's see, pi over 2 divided by 3 would be pi over 6. And if k was 0, you'd have plus 2 times 0 pi over 3. So the cube root of 8 is 2. E, that'd be 0, so you get e to the I pi over 6. So that is a cube root of negative 8i, which we'll verify using our calculator here pretty soon. Well, what if k was positive 1? What if k was positive 1? Well, then you would get cube root of 8, e to the I, pi over, oh, it should be negative, I apologize. That was negative pi over 2 divided by 3. So this would be negative pi over 6. This would be negative pi over 6. Almost lost my negative there. So this would be negative pi over 6 plus 2 times 1 pi over 3. The cube root of 8 is 2, so it would be 2e to the I. And then negative pi over 6 plus 2 pi over 3. That would be 4 minus 1 would be 3, or it would be pi over 2. Pi over 2. So you get 2e I times pi over 2. So that's another cube root of negative 8i. And then let's do when k equals 2 and see what we get. So we get cube root of 8 e to the I negative pi over 6 plus 2 times 2 pi over 3, which comes out to be 2e. Let's see. That would be 7 pi over 6. So it would be I times 7 pi over 6. So that'd be another cube root of 8. Now, you may remember from algebra, your study of the real numbers, that an equation like this, z cubed equals negative 8i, we should expect 3 answers. Well, we have 3 answers now, so the question is that it? Are those the only 3? Are there 3 cube roots of negative 8i? So intuition says there are, but let's convince ourselves that if we kept going, we would just get repeated answers. So when k equals 3, you'd have cube root of 8, no surprise there, and it'd be negative pi over 6 plus 2 times 3 pi over 3, which would be 2e, and you'd have negative pi over 6 plus 2 pi, so that would be 11 pi over 6. So if you take negative pi over 6 and add 2 pi to it, that's the same thing as just negative pi over 6, which we already had. So you'd have 11 pi over 6. But these are the same. These are equivalent. So this is the same as when k equaled 0. Because 11 pi over 6 and negative pi over 6 have the same terminal side. And their moduli are equal. So we've got our 3, and if we kept going, we would just get repeat answers. If we did k equals negative 1, negative 2, again, we would just get equivalent repeat answers. So we've got the 3 that we need. We've got the 3 that we need. All right, so there's our 3 cube roots. Here they are in all their glory, right here. So those are our cube roots. Now, let's go ahead and plot all 3 of those on the complex plane. Let's plot those on the complex plane and see what happens. So here's the complex plane. So I, R. Our first one, we have 2, so the distance from the origin is 2, and our angle is negative pi over 6. Negative pi over 6. So negative pi over 6, that's negative 30 degrees, so that'd be down here. If we go a distance of 2 away from the origin, a distance of 2 away from the origin. So again, I'm not going to try to be exact here. But if we go a distance of 2 away from the origin, 1, 2, let's say it's right here. Actually, I'm going to make that a little bigger. Let's say our distance of 2 is way out here. So basically this right here is a distance of 2. That's what I'm going for. Now, another cube root of negative 8i is a distance of 2 away from the origin, but at an angle of pi over 2. Pi over 2. So I got to go the same distance away. I go the same distance away, so it'd be, up here somewhere. Just trying to eyeball it. So this would also be a distance of 2. Not perfect. And then our third and final cube root is at an angle of 7 pi over 6. So that would be 210. That would be over here. And again, it needs to be the same distance away. So a distance of 2. So they're all a distance of 2 away from the origin. So now let's get rid of all this stuff I used to help draw it. Now, again, I didn't use a rule or anything, so it's not perfect, but notice what we get. Let's draw Let's draw a circle. Let's draw a circle whose center is the origin and has a radius of 2 here. So we got that circle. So those points are all exactly 2 units from the origin. And then if we connect them, we get a three-gon or a triangle. Specifically a regular triangle. So it's a regular three-gon. So we have a regular three-gon, which is a triangle. And as you'll see, that's no coincidence. So the vertices here, so this point, this point, this point, those are our cube roots of -8, and they, when connected, form a regular polygon. In this case, a regular three-gon because it was cube roots. All right, so we were finding the cube roots of -8i, which was given to us in rectangular form. But we have our answer in exponential form. And there's nothing wrong with that, but what if we want them in rectangular form? So our cube roots are 2e to the -I pi over 6. That was our first one. And in rectangular form, that'd be 2 times cosine of -pi over 6 plus I sine -pi over 6. We gotta go to polar form first. So that'd be 2 times, let's see, -pi over 6 be √3 over 2 minus 1/2 I. So we'd get square root of 3 minus I. And then 2e, the second one we got was I pi over 2. So it'd be 2 cosine pi over 2 plus I sine pi over 2, which would be 2 times 0 plus I, which would be 2I. And then our last one was 2e to the I 7 pi over 6. Cosine 7 pi over 6 plus I sine 7 pi over 6, which would be 2 times -√3 over 2 minus 1/2 I, which would be -√3 minus I. So there's our cube roots in rectangular form. Now, to check our answer, we could do it several ways. Let's say you have the rectangular version. So let's say we wanted to check, square root of 3 minus I and see if that's the cube root of -8i. So we could just go square root (3) minus I and cube that. So if we cube it, it should come out to be -8i. Now notice, because of the radical, it gave us kind of a goofy looking number, but it actually didn't. So if you look closely, this is scientific notation. So this is 2 times 10 to the -13th, which is essentially 0. So you have 0 minus 8i, which is -8i. So that verifies that that is a cube root of -8i. And you could repeat that for the other two, by the way. I just showed you how to do one. So real quick, let's talk about notation. As we learned in algebra, if you raise something to the 1 over n power, like 1/2, 1/3, 1/4, 1/5, so n would be 2, 3, 4, 5, 6, 7, 8, 9, and so on, that represents the nth root. Well, in the complex number system, if you have a complex number to the 1 over n power, that's going to denote the set of all nth roots, so all of them, so all the square roots, all the cube roots, all the fifth roots, all the eighth roots, whatever. So what if you just wanted the principal root? What if you just wanted like the main one? So that, there's 2 square roots of every complex number. There's 3 cube roots of every complex number. There's 8 eighth roots of every complex number. So we have to designate, we don't have to, but we've designated one the principal root. And that's actually the one that the calculator returns to you when you ask it for a root. So on the calculator, if I ask this calculator for the cube root of -8, I, which is what we just found by hand, it actually is only going to give me one answer. It gives me 1.73 minus I. It just gives me one answer. Well, the answer it gives me is the principal root. It doesn't give me all 3. It gives me the principal root. So, by the way, to make your calculator return that value to you in your settings, oops. I'm in the wrong part, sorry. In your settings, you have to have real or complex. You have to have the option changed to rectangular instead of real. If you have it set to real, it won't give you a complex valued answer, a non-real answer. So you have to have it changed to rectangular. And you always want to be in radians because we almost always are using radian angles for our arguments. So when you ask your calculator for a root of a number, it's always returning when you have it set to complex mode, it's always returning the principal root. If it's in real valued mode, it's only just going to return a real value back to you. It might not be the principal root, but it's going to be the real valued root if there is one. All right, so what is the principal root? Well, it's the one that you get by using the principal argument and k equals 0. So back up to the one that we just did, we did use the principal argument, which was -pi/2, and when k equaled 0, this is the one we got, 2e to the -i pi/6, which down here was square root of 3 minus I. So this is the principal value right here. So this one, that's the principal value, and that's the one the calculator returns to you, square root of 3 minus I. So when you ask it for the cube root of -8i, it gives you the principal value, square root of 3 minus I, which is this one right here. Now, graphically, the principal value is the root that, when plotted, is closest to the positive real axis, and if there's a tie, it's the upper one. It's the one that's above it. So if you plot all the nth roots, the point when plotted that's closest to the positive real axis is the principal value. So this is our principal value right here because it's closest to the positive real axis. Now if there's a tie, say there's one above it that's also the same distance away, then it's the one above it that's the principal value. All right, let's do one more example. See if we can't make a little bit more sense of this by doing one more. So we want to find 1 to the 1/4. So by raising it to the 1/4, I'm saying that I want all 4 fourth roots of positive 1. Okay, so basically find all z such that z to the 4th equals 1. So we need to find all 4 numbers that when raised to the 4th come out to be positive 1. All right, so if we plot that number on the complex plane, It'd be right here. And that would be the angle in standard position that contains that. So that would be 0 radians or 2 pi radians or 4 pi radians or negative 2 pi radians, any one of those. But let's go ahead and use the principal argument. So the principal argument of positive 1 is 0. Its modulus would just be 1. So in exponential form, we would have we'd have 1 e to the I 0 plus 2k pi power, where k is any integer. So now let's do its fourth roots. So its fourth roots, we would do the fourth root of 1, the principal fourth root of 1, times e to the, and then we'd have 0 divided by 4 plus 2k pi divided by 4. So if you do k equals 0, let's start with k equals 0. Well, the fourth root of 1 is just 1. If you plug in a 0 here, this is 0 plus 0 is 0. You just get 1e to the 0, which is just 1. And that's the root that we would recognize from the real number system. If I ask you for the fourth root of 1 prior to complex numbers, you would just say, well, it's 1. 1 to the fourth is 1, and there it is. Well, what if k equaled 1? Then you'd have 1e, that'd be 0 plus 2 times 1 over 4, that'd be pi over 2. You get I pi over 2. And what if k equaled 2? You'd have 1e to the I. If k equaled 2, you'd have 2 times 2 is 4 over 4 is 1, so you'd have pi. And what if k equaled 3? You'd have 1e to the I. You'd have 6 over 4 would be 3 halves, so it'd be 3 pi over 2. So there's all the fourth roots in exponential form of positive 1. But we started with rectangular form, so let's go ahead and finish with rectangular form. So if we write all these in rectangular form, well, this one's already in rectangular form, positive 1. This would be cosine pi over 2 plus I sine pi over 2. And cosine of pi over 2 is 0, sine of pi over 2 is 1, so you get I. E to the I pi is negative 1, but if you don't remember, you can just go back through polar form. And you get negative 1. And then here, if you plug in 3 pi over 2, let's see, we're going to get 0, maybe negative 1, you're going to get negative I. So our fourth roots are negative I, 1, and negative 1. Now if you plot all these on the complex plane, we should get a regular rectangle, a square. Regular foregone. So 1, 2, 3, 4. Let's say that's positive 1. 1, 2, 3, 4. That'd be negative 1. 1, 2, 3, 4. 1, 2, 3, 4. So you'd have a point there, 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 and there. This would be the circle that they all lie on. And if you connect them, you get a square. You get a regular foregone. Now the principal root would be the one where k equaled 0, and we use the principal argument. The principal argument was 0 radians, and then when k equaled 0, we got 1. So 1 is the principal fourth root. So this one right here, that's the principal fourth root. That positive 1.